So again, in the spirit of these videos, I'm going to give you an alternative proof for theorem 4.7. So the size of every connected graph of order n is at least n minus 1. So how do we prove this? Well, the book again uses some intricate, like some induction, tries to delete something, tries to go bigger or whatever. We're going to make this our life actually a lot easier. So proof. And what we're going to prove is that actually every connected graph contains a tree as a subgraph if I delete only edges. So I can delete edges in every graph until I have a tree. And that means after deleting edges, I have n minus 1 edges, meaning I have to start with at least n minus 1 edges and I'm done. So how does it work? If G contains a non-bridge, delete it. Okay, so then if I do that, G minus E is still connected. And we repeat this process. Repeat until all edges are bridges. This has to happen at some point, right? Because there's only a finite number of edges, and if I repeat this process, deleting an edge after time after time after time, eventually I have to stop. Deleting a non-bridge does not disconnect my graph, so I'm always sticking with a connected graph. I keep the same number of edges, so I have to end. And if my graph is connected and has only bridges, it's a tree. And this tree has n minus 1 edges. And we're done. So this is actually a much easier proof than the proof in the book. And it doesn't really require setting up an induction or so. This is more algorithmic like that. One note maybe is that you really have to do this step by step. Because if I delete a non-bridge, an edge that may have been a non-bridge before I deleted it is now a bridge afterwards. So if I draw an example here, right? So a simple example could be if I start with a cycle, right? In a cycle, every edge is a non-bridge because every edge lies on a cycle, right? That was our definition of bridges, or our theorem that says an edge is a bridge if and only if it lies on a cycle. But if I delete any of them, any of those non-bridges, like so, now suddenly no edge lies on a cycle, so everyone is a bridge, and I'm left with a tree. So that's why I have to do this non-bridge by non-bridge. I cannot delete several non-bridges at once in this argument. I cannot just say delete all non-bridges, because then I may have just deleted all edges and I have a disconnected graph. The only place where I'm sure that I stick with a connected graph after deleting non-bridges is if I only delete one. That's why I have to do all these steps.